Hello everyone and welcome to a new discussion which is on porosity. Earlier we have briefly discussed, so now we will discuss in detail about what is porosity. So that you know that is a rate of volume, basically it is a ratio. So that the rate of volume of void spaces in a rock or sediment to the total volume of rock or sediment. So, it is a ratio between what is the total volume of void spaces in the rock and total volume of the rock itself, and that determine our porosity. So, if the more voids are there, porosity is estimated very high. If less voids are there, porosity estimated very low. In some literature you may find that porosity is defined like porosity, and sometimes it is written as nu or rho of a rock can be defined as percentage of pore space within a given volume, or it can be expressed through equation that is nu equal to V upon Vt and multiplied by 100, because as I have said it is a ratio. So, in percentage you can get the porosity. So, that is the volume of voids, and that is the Vv, and then Vt is the total volume of rock and or sample, or because sample here written that it can also be tested in the labs also. So, generally it is tested in the labs about the porosity, but in a natural situations it is just estimations of what kind of porosity is there, and you take a sample and then it can be also tested in the lab. So, porosity may also be expressed as that is rho equal to Pm plus Pd or rho m plus rho d, and whereas 1 minus we can also write this equation like this. So, where the rho m is the density of mineral particles, and here is the rho d is the bulk density, and then porosity can also be expressed in percentage, because in earlier equation we have seen that we multiplied by the 100 on the right side. So, that this equation or any equation can be also expressed in percentage. Basically, as I have already said, it is a ratio. On the right side we are seeing two schematics or two figures. One is having pore spaces which are very large, and on the right side we are having pore spaces which are very small. So, that definitely on the left side the porosity is going to be very high. Generally in sediments or sedimentary rocks, porosity will depend on the grain size, shape of the grains, and the degree of sorting and degree of concentration. So, we will take one by one. If a grain size is larger, then there are chances that we will have more porosity. If the shape of the grains, that means if these are the rounded shape grains are there, sediments, then we will have more porosity. But if it is a more flat kind of grains are there, then there are chances that we will have less porosity. Further, the degree of sorting, if all sediments within sedimentary rock or in a sample are well sorted, means having almost same size, then porosity would be very high. But if sorting is poor, then porosity is going to be less. How? Because smaller particles will fill the gap or the voids which is in between of larger particles. So, if I take example here, that if on the left side figure, if smaller particles would have been there, that means poor sorting, then these smaller particles will fill the voids, and therefore, it will reduce my porosity. And degree of cementation, that means because all the time we are not talking about the loose sediments, we are talking also about the sedimentary rocks. So, sedimentary rocks will have some cementation material which will keep grains intact. So, if a degree of cementation is very high, again porosity is going to be less, but if degree of cementation is not that high, then porosity would be more. So, it depends, the porosity depends on many factors, that is grain size, shape of the grains, degree of sorting and degree of cementation. This is in case of sedimentary rocks or sediments, loose sediment. So, just for completeness, for example, a well-rounded coarse-grained sediment usually have higher porosity than fine-grained sediment, because the grains do not fit together well. And poor sorted sediments, that means you are having large sediments and fine sediments together, usually have lower porosity because the fine grained fragments tend to fill in the open space. As you can see here, earlier also I was trying to demonstrate the same thing. And since cement tend to fill in the pore space, so degree of cementation, that is the highly cemented sediment rocks definitely is going to have low porosity. And the spaces are known as voids, which we have been using this term, or interstices and or pores or pore spaces, depending on the types. Like in case of basaltic rocks, a large part of India is being occupied by basalt, and there we say vesicles or voids. But in case of sedimentary rocks, we say pores or pore spaces, or in case of hard rocks, we may call as interstices, that is the gaps between different grains or minerals are there. So, well cemented like here, the well cementing is done, degree of cementing is high and therefore less porosity. So, interstices are fundamental to groundwater studies because these serves as water conduits, that means from through which the water flows. So, if more pore spaces are there, if they are connected, that is what interstices, that means interconnection between these pore spaces. If that is there, then it is important or useful in the groundwater study, because they serves as pipes kind of, or flow, they allow the flow of water from one end to another. And typically these interstices are characterized by their size, shape, irregularity and distribution. So, it is a almost same kind of scenario as in case of sediments or sedimentary rocks and grains. So, the size of interstices will depend. If size is large, you are having better flow of water. If shape is also important. So, if it is just like a narrow tube, then definitely because of surface tension of water, the flow would be less. But if shape is larger or larger kind of pipe, then more better flow will have. Irregularity, how regular these shapes are or irregular interstices are, so our porosity will also depend in case of hard rock terrain, and how these are distributed within a rock mass. And so, original interstices and pores or voids are created by geologic processes. Some porosity is inherent or genetic porosity, you can say, that when these rocks were formed, then at that stage the porosity occurred. But there is also a concept that is called secondary porosity. Later on, because of weathering or some other geologic processes, further porosity can be found in the rocks. That is what we consider as secondary porosity. So, there is a genetic porosity or time of geologic formation of rocks. Like here, we are giving the poorly sorted sediments example, of course, cemented examples. Now, like examples, sedimentary rocks we have taken, the example of sedimentary rocks we have taken in case of sediment porosity, but if we take example of igneous and sedimentary rocks, the porosity is usually low. Why? Because you do not have the like grains and pore space in between and so on. Whereas in these rocks, these are what we call as hard rocks like igneous and metamorphic rocks, porosity is low, and because the minerals which forms these rocks tend to be intergrown, leaving very little free space, and no interstices generally are there at the time of formation. However, the secondary porosity with the time, in geologic time I am talking, may develop with these rocks. So, highly fractured igneous and metamorphic rocks or highly weathered igneous and metamorphic rocks can have some kind of porosity, and sometimes they are having also high porosity, as high as like in sedimentary rocks. But it depends on the fracturing of the rocks and also the weathering of rocks. And so, those portions of rock or soil not occupied by solid minerals, matter can be occupied by groundwater. So, if those spaces have been left open, then these, if they are interconnected, then these can be also occupied by the water or groundwater in case of groundwater situation. So, like here I have already said that the primary porosity or genetic porosity or porosity created at the time of rock formations, and so that is the first example is here, that is primary porosity, pores, spaces between grains. You can see here that all these are there, though the rocks are or the sediments here are poorly sorted and not well sorted, but predominantly you are seeing larger grains. Secondary porosity it develops later on, like on the bottom part here you are seeing the secondary porosity. So, this is the because of fractures or some weathering processes, a secondary porosity in hard rock like igneous or sedimentary rocks may develop. Now, the third is the effective porosity. So, like how much really it is important from flow point of view, and that kind of porosity we consider as effective porosity. So, we define here one by one with the proper definitions, that the primary porosity is the original porosity of the rock when it formed. So, that is why I said a genetic one. Secondary porosity, however, is the pore spaces created by subsequent processes such as fracturing, jointing, solution opening, that means weathering, opening created by plants and minerals. So, those kind of things can create secondary porosity, and in many old rocks, igneous and sedimentary rocks, one can always find secondary porosity to sometimes to a good or larger extent. Further, secondary porosity with respect to the size and interstices may be classed as the capillary, depending on capillary when the size is very small, or supercapillary, then and then third one is the subcapillary. So, even smaller than capillary, then we are having subcapillary. If it is larger than capillary, basically capillary, when we say, it is all controlled by the surface tension of the water, and you know that the surface tension changes, surface tension of water changes with the temperature also or impurity. So, some of these things in absolute terms cannot be measured or estimated, but they helps us in terms of groundwater flow or groundwater storage. So, secondary porosity or these capillary things which we will see, that capillary is the interstices are sufficiently small where surface tension forces will hold water within them, that is what the capillary is. And second one is the supercapillary. Interstices are those larger than capillary ones, so that the water can move through supercapillary system very fast, and subcapillary, which are the interstices, are so small that water is held primarily by kind of a adhesive force, or because of basically viscosity is there, high viscosity, and because of narrow channels are there. Secondary porosity can include fracture porosity, space within the fractures in any kind of rock. So, fractures can also be in sedimentary rocks, but sedimentary rocks generally depending, but they may have their own porosity at the time of origin. So, some volcanic rocks, I gave example of that basaltic terrain, that is Deccan Trap area of India, which is like a large part of Maharashtra, Madhya Pradesh and Gujarat is covered by Deccan Traps or volcanic rocks, that is basalt, has a special type of porosity related to vesicles, and some limestone terrain also has extra porosity related to cavities within the fossils. So, that means the cavity is created because of erosional activity. So, the big caves can also be found, but limestone terrain, and I would say the study of groundwater in limestone terrain is really challenging. Finding the water, estimating the or doing the pump test and other things is very, very challenging. Anyway, so in volcanic rocks, I have been mentioning that the porosity is generally related to vesicles. These vesicles are nothing but the gas which we are trapped and now left. Some of the vesicles, because of secondary enrichment or mineral enrichment may filled with the like quartz and other things, but others are fine. So, this is the one of the examples of porous or basaltic rock, which is having lot of vesicles, which you can see here. Sometimes you may find that they are filled with another mineral like quartz or amethyst quartz kind of thing, but normally they are not. And if they are, these vesicles are interconnected, that means if interstices are there or fractures are there, then they may allow us to, they may have some storage of water, and that water can also be withdrawn. So, now we come to the effective porosity. Effective porosity is the amount of interconnected pore spaces, because this discussion we have been having that a rock can have high porosity, but it is not necessary that it will have a high permeability, because if these pores are not connected, then water might be there, but it is not coming out. So, that can be measured about the porosity through this concept of effective porosity, that is the amount of interconnected pore spaces available for fluid flow, and is also expressed as a ratio of interstices to total volume. So, generally it is presented in the form of percentage, that this such and such rock having porosity of this much. So, the examples of a few types of rocks are given here about the intensities and the relation to rock fractures to porosity. So, we will take one by one. Here on the left, top left, we are having the well sorted sediment deposits having high porosity, and you can see that all are having high porosity, but here on the top row right side, the rock tendered porous by solutions, that is we are talking about a limestone terrain where the solution activity take place and that kind of thing. But first two are the more or less well sorted sediments, and you are having a good porosity here, whereas a next two means the B and D are the poorly sorted sediments deposit having low porosity, and rock rendered porous by fractures. So, maybe in case of igneous rocks or metamorphic rocks, such situation may occur. And a C part, especially this one, is the well sorted sediments, which we have already discussed. Deposits consist of pebbles that are themselves porous, so that the deposit of a well highly porosity. This is another very important thing, that because after all these, if you are having large grains, well sorted material, the grains itself may be coming from sedimentary origin or sedimentary rocks. So, they too, and the individual pebbles or cobbles or boulders are having their own porosity, and therefore, the effective porosity is going to be very high in case of this scenario C. Similarly, in case of scenario D, the well sorted sediment deposits whose porosity has diminished. Why? Because the deposition minerals in the interstices. So, the second mineralization or cementation has occurred, and therefore, the effective porosity is going to be very less. So, these are the 6 examples of 6 different types of scenario, but in nature many such scenarios can happen. The important point here is, like as we have discussed, the porosity will depend on the type of rock, sorting of rock, grain size, and in spaces, cementation, degree of cementation, all those things. And in like a limestone terrain, which is again sedimentary rocks, you may have the solution cavities, solution fractures, and another one in case of igneous or sedimentary rocks, you may have the porous by because of simple fracturing or jointing. So, in terms of groundwater supply, because after all these we are discussing from groundwater point of view. So, for in terms of groundwater supply, granular sedimentary deposits are of major importance, but everywhere we do not get such rocks. So, we have to find the water, groundwater in all types of rocks, no matter how, what is the quantity of water. But anyway, the best ideal situation is that we should have a granular sedimentary deposits. Porosity in these deposits, that is in granular sedimentary rocks, depend on shape and arrangements of individual particles, distribution of size, degree of cementation, and compaction, how compact these rocks are. And in consolidated formations, removal of mineral matter by solution, like in case of limestone, and degree of fracture are also important. So, they basically all these are influencing our porosity. So, what we can say at this stage, that the porosity range from near zero, in no porosity, completely unweathered, unfractured hard rock is there, maybe a batholith granite kind of example, to more than 50%. 50% is really very high porosity, but it will depend if it is a conglomerate and other things, and cementing material is not there, but grain themselves are sedimentary rocks, coarse-grained rocks, then porosity may reach to up to 50%, but it is very rare. So, the range roughly we get around 0 to 25 or 30%, depending on the factors which we have just discussed, the particle size, distribution, sorting, cementation, and type of minerals also or materials also. So, in sedimentary rocks, porosity decreases with the depth due to compaction. So, on surface some sedimentary rocks may have higher porosity, but as you go deeper in the bells or excavation, you find less porosity. Thus, a typical relation also exists, that alpha z equal to alpha 0 and E power minus a z. So, here this alpha z is the porosity at depth z, because we are talking about now elevation. So, therefore, the z is there, and A0 the porosity at the surface, at the top of the surface where the z value is 0, and then A is of course constant here, and E is the base of Neperian logarithm. So, that can give you the estimates about the porosity also. Now, say average things are presented here, that if we take the volcanic rocks and if these are fractured, then we are having in this extreme we can have a between 40 to 50% porosity. Similarly, in case of limestone, of course, our porosity is going to be further high. In case of mudstone is having more clayey material, and therefore, porosity is going to be 30%. In case of sandstone, and that too the well sorted and less cementation, our porosity can be 30%. As earlier I said, that only in a rare cases we reaches to the 50% porosity, otherwise the things are ranging between 20 to 30%. In glacial till, because these are poorly sorted material, maybe very poorly sorted material, and therefore, porosity is around 20%. In case of conglomerate, I gave example just few seconds back, that a conglomerate is relatively having higher porosity, because you may not have good cementation and the grains themselves might be having sedimentary origin. And there are unconsolidated materials are there, loose sediments are there. So, like silt and clay, they may have even up to 70% porosity, but again repeating, high porosity does not mean that it will allow water to flow from one end to another. In case of sand, the porosity may be less, but the sand will allow water faster to move from one end to another. So, that means the transmissivity is going to be high in case of, whereas gravel again porosity may be less, but they are better than even the sand, loose sand. So, these are the unconsolidated material, and these are the solid rocks examples in blue color. So, the ranges in porosity of a number of different geological materials which we have seen. And so, more basically they are all ranging between maximum in the rock, solid rock rocks are ranging between 0 to 50%, and unconsolidated material can range even from 10% to 70%. So, further on this unconsolidated sediments that tend to have higher porosity because the compaction has not taken place, and consolidated ones because there is no cement and most have not been strongly compressed. So, compactness is not there, and therefore, it will have high porosity and sometimes also high permeability. Finer grained materials, for example, silt and clay, tend to have greater porosity, and some as high as 70%, we have seen in previous slide, and then the coarser material, for example gravel. But from water flow point of view, gravels are more favorable than silt and clay because of grain size. Primary porosity tends to higher in well sorted sediments compared to poorly sorted sediments, because poorly sorted sediments, the space or pore spaces will be filled with finer grained sediments. So, where there is a range of smaller particles to fill the spaces made by larger particles. Glacial till example we have also seen in the previous slide, that it is poorly sorted, and therefore it may have wide range of grain sizes, and typically formed under compressed beneath glacial ice, has relatively low porosity. Consolidated and cementation during the process of lithification, when sediments goes towards the rock formation, that process is called lithification. So, in case of unconsolidated sediment into sedimentary rocks reduces primary porosity. So, loose sediments will obviously have more porosity, but if compaction occurs, lithification occurs, it reduces further your porosity. But the primary porosity, when we find a material, at that time whatever the porosity is there, we say, or if weathering other things are there, which we have already said about that. Sedimentary rocks generally have porosities in range of 10 to 30%. Examples we have seen. Most of these are ranging between that, and some which may be having secondary fractures porosity also. So, overall effective porosity in that case, if they are having fractures or even weathering, they may have higher porosity. Further, grain size, sorting, compaction, degree of cementation, rock all influences primary porosity, and this we have already discussed. In case of igneous and metamorphic rocks have lowest primary porosity, because during their formations hardly there are, except in case of volcanic rocks where we may have the vesicles, otherwise they are having interlocking crystals. So, generally in hard rock terrain or in hard rocks, igneous and metamorphic rocks, what we are talking, whatever the porosity which we are talking, is many times it is the secondary porosity, that too has been created because of fractures and joint planes. Whereas of consolidated rocks, hard rocks, well fractured volcanic rocks and limestone has cavernous openings and produced by dissolution. If solution activities are there, then obviously the porosity is going to be high. In case of intrusive igneous rocks or metamorphic rocks which are formed under the ground, then there are great pressure and will have lowest possible porosity. They are the like batholith example I have been giving, that these are the really plutonic rocks, they are formed much lower or much deeper in earth. So, porosity, as you know, is a measure of how much water can be stored in geological materials. This is what is important thing. The ratio is fine, everything is fine, but how much water it can be stored in a geologic material. So, now we are reaching almost end of this discussion, that almost all rocks contain some porosity and therefore may contain water. And this is what the point which I was saying, that gravelly sedimentary rocks not necessary to find everywhere, and we know that they are not there. So, we have to find water in all kinds of geological formation. So, in that case it helps this statement that almost all rocks contain some porosity and therefore may contain water. And considering that sedimentary rocks and unconsolidated sediments cover about 70% of the continental crust with an average thickness of few hundred meters, and they are likely to have around 20% porosity on average. So, it is easy to see that a huge volume of water can be stored in the ground. So, this will help us when we will discuss the groundwater recharge, which is very much required now in this country, because we want to reduce the surface runoff and we want to solve the groundwater problem. So, this kind of 20% porosity if is there, average porosity, it is really very good and a sufficient amount of rainfall is there in some area, then we can definitely recharge the groundwater regime. So, with this I end the discussion. More details can also be found on this side. So, I am giving reference. Thank you very much. Bye bye.